So today we're talking about the analysis of aerodynamic workflows, in particular the preparation of data for the high lift prediction workshop, which will be held this summer. I'm Scott Emlay. I'm the goofy guy on the right. And I will be asking the questions and acting as host today. Devin Simpson is our product management representative, and she will be answering the questions today. This is a brief overview of what we're planning to do. We want to review what the post-processing requirements are for the high lift prediction workshop and how to automate, what are some of the best practices for automation. And then we will go through your list of questions and I will be asking them on your behalf. So, Devin, what is the high lift prediction workshop?
So, June is the third of the high lift prediction workshops, and they were started to try to assess and enhance the current state-of-the-art of CFD capabilities, particularly with high lift aerodynamic design, optimization, and such. So for this particular workshop, participants are required to work with two different models, the JAXA standard model, JSM, and this is run with and without a nacelle pylon attachment. So the image on the side is the JAXA standard model without the nacelle. And then the second configuration is the NASA Common Research Model, which is in the high lift configuration, so the HLCRM as an abbreviation. So.
And we have data for some, or they are offering data for some of those now, right?
Correct. So we have the grids and some of the data associated with those files.
Okay. The participants will be comparing against experimental data?
Correct. We will be, the JAXA wing has been run in the wind tunnel, and the high lift configuration of the NASA Common Research Model will be run in the wind tunnel by the end of the year.
What data are participants required to submit?
So there's four elements of the data. The first two, the iterative histories and the total forces and moments, are usually supplied as an output to the CFD solution being when they're run through the solvers. So in this presentation, we're really going to be concentrating on the extraction of data from the full surface and volume solution from CFD. So in this case, the committee is looking to compare CP and CF extractions at specific spanwise locations. These were defined for both the JSM model as well as the Common Research Model. And these would be compared directly to the wind tunnel data at the pressure taps locations from the wind tunnel. So that's to compare directly to CFD. Whereas the velocity profiles, we're given specific XY locations on the wing to extract up in the Z dimension. This is going directly up in Z all the way through the wake. And the velocity profiles are really looking primarily at comparing CFDs to CFD. So seeing how the velocity is built up through the wake.
So CP and CF, those are coefficient of pressure and coefficient of skin friction, correct?
Correct.
And you said that the velocity profiles are extracted in the Z direction, so they're not surface normal.
No, they're directly constant X and constant Y.
Thank you. How can I automate the CP and CF wing slice extractions?
So the Tecplot 360 has two different ways of automation as of 2017 are: one, we have PyTecplot, which is our newest scripting library, which uses the power of Python along with direct access into Tecplot 360. And then there's the traditional Tecplot macros, which have been part of the product since the beginning. You should be fairly familiar with that. The High-Lift Prediction Workshop Committee has actually provided Tecplot macros to do the slice extractions along for both the JSM and the high-lift model at their specified locations. But macros have they're fairly rigid, and all of the macros will require some manual editing between solvers. So specifically, they're looking to have, say, coefficient of pressure and coefficient of skin friction you have to know which variable number or position they're in to have these macros run properly. So they're also harder to run in batch, as you have to supply the data file and the macro file associated with them, and you have to have the data already loaded or in some manner to be able to run the macros.
How do I write scripts which work with different grid and solution formats?
So to have it work across multiple grid and solutions, which the High-Lift Prediction Workshop is really looking at comparing different solvers and grid densities, the best tool is to actually use the power of the Python language with PyTecplot. And PyTecplot launches 360 in batch mode and gives you the access to all pure Pythonic functions like for loops and string processing, in addition to the access directly to the 360 engine. So here's an example where I'm searching the full data set by looping over the data set to search for a particular var name. So different solvers have different variable names outputted. So some might have CP, some might be coefficient of pressure, some might be pressure coefficient, or some variety thereof. And so in this case, we're using a list of strings to find the best match in the data set, and then returning a variable object which can be handled throughout the rest of the data set natively using PyTecplot. So this is a Python object with access to the variable in the engine by searching through these keyword variable names.
Okay.
So this can be done somewhat in the macro language too. Instead of indices, using a name can be more powerful. You can most actions can actually accept a name in addition to an index. So that can allow your macros even to be more general. But for the most part, we highly suggest going to Python if you're needing this flexibility between grids and solution formats. One final thing to note is that when performing extractions like this, Tecplot actually keys off active zones. So what I mean by active zones is if you're in zone styles, the zones that are actually on or showing in the plot are the ones that it will be extracted from. So if you've got if you're doing a surface extraction, and you might be hitting both the nacelle and the wing at the same time, and the extraction will go through all active zones. So this is something that you want to be aware of while writing scripts, particularly if the grids are broken up differently between different solvers. You might be getting additional zones when or additional sections of zones while extracting.
So for instance, an outer boundary or a tail, you
Right.
want to make sure those are turned off.
If you're concentrating on extracting surfaces from the wing, yes.
Okay, excellent. How do I automate slice extractions in a more generic way?
So extractions are pretty powerful in the Tecplot language. This is a sample PyTecplot script where we're given a Python dictionary of a slice name, an origin, and a normal. This is an abbreviated list, only showing one, but the image on the right, you can see that I actually looped through and I did about 20 sectional cuts at different angles and normals. I then supply several files to loop through, so I can do different grids, different cases at the same time over multiple files. This can, in the examples provided, this will be a command line option instead of hard-coded. But for demonstration purposes, we'll be looping through 2 of the JSM cases, making sure that we've got fresh by doing a new layout between the files, then loading CGNS with the boundary conditions included. They'll be turned off actually by that parameter. Then we also want to make sure that Cartesian 3D is our plot type, because slicing only works when we're in a 3D plot type. From there, we'll go through the sectional cuts list dictionary for the name and location, extract the slice with the origin and normal as defined above, and then we will be slicing through only surface zones. At this point, we'll use the PyTecplot language. This is a zone object, so we can rename it directly with the file name and the name of the slice. So create a list, and then this line is creating a list of zones to export. And finally, we will be saving a Tecplot ASCII file in point format, using only zones, exporting only the zones that were extracted.
And the Tecplot ASCII format is what the committee requested the data be submitted in.
Correct. So specifically ASCII with point format is what the committee is expecting to be submitted.
So if they run the script, this ASCII file can be submitted directly to
the file name might need to, or the file name or the zone name might need to be modified slightly to make sure that it's exactly the format of the zone name that the committee has requested, but it is very, very close.
Okay, excellent. What is the best way to extract line data from a volume? So this would be for the Z profiles, velocity profiles, right?
So to do this, there's actually 3 different methods. The first is actually to load in a defined line of XYZ locations and then interpolate from the volume zones onto a line, or the imported line. The second option is extracting a polyline, and by polyline I mean a geometry that's defined in 2 locations. This can be, you can define exact locations of the XYZ coordinates of the polyline in the Tecplot macro language, and 2017 R2 will have a feature called extract precise polyline, where you can define two locations and extract an evenly distributed set of points between those two locations. Note, this capability isn't exactly what we're looking for this case, because it's evenly distributed between the two locations. We're not getting the same kind of grid refinement that you have in the grid given. So this is kind of not necessarily the recommended for this case, but could be the easiest in other cases. The final option is to actually extract a surface slice, which results in a line, from an already extracted 2D slice. So in this case, you'll be extracting once in the y dimension at the given y location, and then to get a 2D slice, and then extracting again in the x direction to get a single line off of that 2D slice. And for the participants registered, we'll be sending out a PyTecplot script, which does option C as well as option A for this process, for both the models. Note that option C really works well with option A. So the extracted lines from one model, you can export those to a data set and then load them into another data set and have the exact same points for every single model. And this could be useful if you're looking to compare the lines between model to model, as the extraction locations will be identical between the two methods.
Excellent. So on the option C, extract a slice of a slice,
Mm-hmm.
how do you make it so it doesn't go to the bottom of the wing as well?
So in that case, the script provided is actually using blanking, where I've probed at the surface. I kind of have to know, you kind of have to know going in where the surface of the grid is going to be and how far into the wake you would like. So that is an input to those files. But since we're going for the same extraction from model to model, this is constant, or it should be fairly constant. Although we did have to define a specific location very close to the surface, and then using blanking because the wing changes z direction throughout, so we didn't want to lose any of the boundaries there.
Okay, so you just blank just inside the surface a little bit, and then you blank at an
arbitrary extension.
Excellent. Thanks. How does the code handle data in overlapped regions, say from an overflow data set or something?
So in this case, you definitely want to use blanking variables if they're available. Most overflow solutions will have an iBlank variable where we will turn on blanking. And even with iBlanking on, there'll be still some cell overlap. So a note for those using the committee's macros, you would have to add this blanking element and actually the PyTecplot macro scripts being provided. You will have to add this blanking parameter to make sure that you're extracting only the cells that you're looking at, that the solver used. So at the boundaries, there will still be some cell overlap. So in those cases, the behavior of 360 will actually depend on the action performed. So if you're probing, interpolating, or doing an extraction, it's actually the first cell of the first zone encountered. So it goes through, and the first cell it finds, or goes through the zones in ascending order, and the first zone it finds, that's the one it will use. And then, however, when you're, say in the case of rendering a 2D slice, it will actually be showing both cells in that region. So there might be some graphical issues there, but it should be a very small region, so you shouldn't notice it.
Okay. How can I work more efficiently with large data sets?
So thank you for asking that. The best and most reliable way for overall performance is definitely using our Sizzle PLT format. This includes reduced memory and increased speed. So from the plot, or from the table on the right, we did a quick test with the JSM case 1, so this is without the nacelle, for a medium unstructured grid. It's kind of the data set you've been seeing in the images throughout the presentation. And then we performed the PyTecplot script with the velocity profile extraction off of the Z direction, and these were the results. So the CGNS file was about 4 gigs. We converted it to both PLT and Sizzle PLT, and there were 4.6 gigs and 2.6 respectively. So you're getting some node compression because there's a lot of triangles on the surface in an FE quad data set. So that point compression is why we see the file size reduction. And then the RAM, you're getting an order of magnitude increase of, or decrease of RAM usage from 13 and 11 gigabytes down to 150 megabytes. And then you're going, for time to extract, you're going from just a few minutes to a minute to only 5 seconds with Sizzle PLT. And the reason behind this is that Sizzle is only looking at loading and looking at the zones very close to the extractions. So when you're doing a volume extraction like this, we're looking at loading a very small portion of the data, whereas with CGNS and PLT, we have to load all of the data in those volume regions.
Yeah, I have just one thing to add to that, or two actually. First is that this works also with, if you have remote data, with the new Sizzle server. So it's to utilize the Sizzle server, you just go to File and then Load Remote Data, and you would be able to get the same benefits even leaving your data on a remote machine. The second is you can convert these files using Tecplot 360 from CGNS to SCPLT, just using the convert flag, and it won't, in batch mode, and it won't check out a key. So you can install Tecplot wherever the data is and do your conversion, and you won't have to have it. It's unlicensed if you're just using -convert.
So a few more tips to use large data if you're using it interactively. The first tip is if you're seeing graphical slowdowns, turn off auto redraw. That's down in the bottom left corner of the plot sidebar. And then finally, there's the options menu and then performance options, where things like plot approximation, graphics clash, and minimize memory use can be optimized for larger data sets.
So when would you use the plot approximations and turn off the graphics cache?
When you have when you're seeing slow rotations or where your graphics card is being the bottleneck.
Okay. How do I convert an existing Tecplot macro to PyTecplot?
So the first step is to check out our documentation at tecplot.com/docs/PyTecplot, and we've got a very thorough description with examples and further questions or further scripts there. Then you can also use the tecplot.macro.execute command, which will execute any macro command that's available in the Tecplot macro language. You can paste that directly as a string, pass that to this command, and it will do exactly as it would in the Tecplot macro language. And then finally, in the next release, we're hoping to have recording from the UI available. This will hopefully be available in the fall, where you can go to the scripting menu and record PyTecplot scripts just the way that you record macros at this point. And then finally, if you need any help, feel free to contact Tecplot support at support@tecplot.com.
So Devin, we have a question online that's related to this, and that is, what is batch mode?
So batch mode is when you're calling Tecplot 360 without the graphical user interface. So you'll see PyTecplot at this point is only batch mode. You can't interact with the 360 interface, and it's doing everything as a silent process on your computer.
So how would they, what does that look like? How do they actually launch Tecplot in batch mode?
So if you're looking to launch Tecplot in batch mode with a macro, you would call Tec360 on the command line with a -B flag and a macro. But for PyTecplot, all you have to do, you would do Python and then supply a Python script, and it's actually the import Tecplot command. So Python libraries are loaded by import Tecplot. So if I go back up to this, the sample script, I have import Tecplot as TP, and that element is actually launching a 360 instance silently on your machine, getting a license and acquiring the license and executing these commands without bringing up the user interface.
Okay, and somebody asked about Tecplot. PyTec scripts work only in batch mode, or can we use them in interactive mode?
So today they're only in batch mode, but along with the recording, we're hoping to have an interactive version of PyTecplot for the fall release.
Excellent.
So that brings us to any additional questions. Scott, do you have anything lined up for me?
Yes, we have one here. It's how do we calculate pressure force data in the entire control volume for 3D cases?
So the best way would be to use, there's two different ways. You can use data alter if you know the equations directly. So this would be found on the data command. You can go to create, specify equations and type in equations using variables already existing. But you could also calculate that via the CFD analyzer menu. So there's an option for calculate variable, and sometimes you have to set up the incoming variables to be able to calculate outgoing variables, but skin friction should be one of the variables in that menu.
Okay, I think the question is actually slightly different. He's asking how to calculate forces in moments, I believe, from the surface. Well, basically, how to calculate forces in moments when you have volume and surface data.
That would also be under the Analyze menu. There's a forces and moments calculations there.
Right, under the integration. All right, integration.
Integration, yeah.
Under forces and under the Analyze menu. Let's see. Do you know any performance penalties by using PyTecplot to execute simple conversions?
PyTecplot, for the most part, we've seen orders of magnitude improvements over the macro language for simple or for advanced scripts with data access, as it has direct access to the engine versus direct queries or having to query the data in the macro language. So for the most part, we don't have exact performance data yet, but PyTecplot is as fast as any other methods in PyTecplot or in 360 as you have direct access to the engine.
Okay, let's go. Is there a way to post-process on the fly, like client-server mode or something similar, that post-processes in parallel and on the fly? You want me to take that?
Yep.
Okay, so there is, we have a client-server mode, but it is not on the fly. It's not an in-situ processing that I think you're asking about. But we are looking at offering a form of in situ. I'm actually presenting a paper on that at the aviation conference this summer, and in which we will write out only the subzones you need, and that will allow you to essentially run your Tecplot in separately. It won't be on the parallel on the HPC system necessarily, but it'll be much faster, and you can post-process while you're running. Let's see, what's some other questions? Is there any PyTecplot scripts to take advantage of transient solutions? Take average of transient solutions. Not yet, but transient capabilities were just, being able to change plot time steps was just added to the PyTecplot API in the latest release, and we could definitely help you create a script if you contact us at support@tecplot.com. Can PyTecplot scripts be used with Chorus?
PyTecplot can be launched by Chorus, but because we are using the 360 engine, Chorus is built on a different engine, and at this time we don't actually have any connection to connection at this point to PyTecplot. But Chorus can definitely use the power of PyTecplot to generate variables and generate images. Okay. Will you send PyTecplot script to participants? Yes, we will be sending, we'll be contacting the committee with the scripts to make sure that they get distributed to the participants, as well as everybody registered for this webinar. Yeah, we will be sending out email letting you know how to get the scripts. We'll probably make them available along with the recording, so and there may be multiple ways to actually get the scripts. Yep. So we should be wrapping up now because this was intended to be a 30-minute webinar, but I have one more question.
Let me make sure I understand. Okay, so this is related to the question about performance penalties. It says, like evaluating the coefficient of drag or other indirect flow properties from the script itself. So is there performance penalties related to that?
No. Using this PyTecplot scripting language, you have access to even data on a point-by-point basis. So you, depending on how you access it, there can be performance penalties, but using using the direct access available in PyTecplot or full array access, it is quite fast and a lot faster than the macro language ever was.
So I think what you're saying is, yeah, if you pull data out of Tecplot into the Python layer, it's faster than the macro. But you can also leave the data within Tecplot, right? And take advantage of Tecplot's speed for doing calculations for those things that Tecplot can actually do.
Right. Yeah. So and by doing it that way, you are at the same speed as it would be, or same or faster speed as if you would be doing it in the UI.
Yeah. So it's taking advantage of you know, all the processors on your system.
Correct.
You know, for those things that have multi-threading, and yeah, so. Good. So we're going to wrap it up now. We actually will, we have more questions that have come in, and there were a few that came in before the webinar that were too late to actually get on the slide deck. We will answer those, and those will be available to the webinar attendees. You know, we'll send them out in an email to you so that you can get answers to all the questions. I apologize if we didn't get to your question, but we will get to it before, you know, fairly quickly. So the Aviation Forum and Exhibit in Denver is where the High Lift Prediction Workshop will happen. It's on June 3rd and 4th. The paper I mentioned is actually going to be on June 7th. At 11:30 a.m. It's a subzone-based in situ technique for IO efficient analysis and exploratory visualization. And go ahead and come by and visit our booth, which is booth number 404 in the exhibit hall. During the exhibit hours, it's June 5th through the 9th. And you know, and there are a few of us will be there. If you want to get together for something, you know, drop us an email, and we can talk to you even outside of exhibit hours. Thank you. I think that's the last slide.
Yep. So.
And if you have any questions, feel free to contact technical support. Thank you, Devin.
Thank you.